this video, we're going to take a look at the concept of indefinite integration. Previously, we have learned the concept of differentiation, which is to find the derivative of a function. Now we're going to take a look at the problem of differentiation in a reverse manner. That means now we are interested in the function before differentiation, but not after differentiation. This concept of reversing differentiation is called integration. The notation of integration is like this. In this example, it means that we want to reverse the differentiation for x squared with respect to x. Now let's try to solve this problem. Let's think about what should be differentiated so that we can get x squared. By guessing, we can know that by differentiating 1/3 times x cubed, we should be able to get x squared. However, we can also know that it is not the only case. Because we know that the derivative of a constant is always equal to 0, so if we add a constant to the function 1/3 times x cubed, we can also get x squared. As a result, there are infinitely many cases that can give us x squared after differentiation. Therefore, we can say that the result of this integration is equal to 1/3 times x cubed plus c, where c is an arbitrary constant. Arbitrary means it can be any number, and constant means that this number will not change with x. We can see that this result is not certain because of this arbitrary constant c. Therefore, this concept is known as the indefinite integration. Indefinite means the result is not certain. Now let's learn some terms in integration. A result before differentiation is called a primitive function or an antiderivative. In this example, these three functions are all primitive functions of x squared. And then the result of the indefinite integration is called the indefinite integral. The function inside the integral is called the integrand. And then the arbitrary constant c is called the constant of integration. Now let's try to understand indefinite integration in formal terms. If we define capital Fx as a primitive function of small fx, that means capital F prime x is equal to small fx. Then the indefinite integral of small fx with respect to x is equal to capital Fx plus c, where c is an arbitrary constant. By this definition, we can immediately have two properties of indefinite integrals. The first property is that when we have addition or subtraction of integrands, then we can split the integrals like this. The proof of this property is like this. We want to see whether the result of differentiating this function will give us this integrand. By this definition, we can rewrite this integral as capital Fx plus c, and we can rewrite this integral as capital Gx plus c. Here we write down 1 and 2 for the constants because the constants may not be equal. For differentiation, we have already learned that we can differentiate the functions one by one if they are connected by addition or subtraction. So we can get that the result is capital F prime x plus or minus capital G prime x. And then by this definition, we can rewrite capital F prime x as small fx, and we can rewrite capital G prime x as small gx. Therefore, we can see that by differentiating this function, we can get back the integrand, and therefore this property is proved. For the second property, it means that any constant inside an indefinite integral can be taken out. To prove this property, we can use the same technique. We can try to differentiate this and see whether we can get back this integrand. We have already learned that a constant can be taken out in differentiation, and then by this definition, this integral can be rewritten as capital Fx plus c. After differentiation, we can make use of this definition, and then we can get back k small fx. Therefore, we can get back this integrand, and as a result, this property is also proved. Next, let's learn some integration formulas for standard functions. We have learned that the derivative of kx is equal to the constant k. Therefore, we should know that the indefinite integral of a constant with respect to x is equal to kx plus c. In particular, when a constant is equal to 1, we can simply write as integrate dx, and the result is equal to x plus c. And then by referring to this differentiation formula of x to the power n, where n is a constant, we can get that the indefinite integral of x to the power n with respect to x is equal to x to the power n plus 1 over n plus 1 plus c. We can understand this formula simply by differentiating this, and then we can get back x to the power n. Please note that n must not be minus 1, otherwise the denominator is equal to 0 and then the whole thing will be meaningless. When n is equal to minus 1, that means we are referring to 1 over x. That means when we are integrating 1 over x, we cannot apply this formula. When we really need to integrate 1 over x, we should refer to this formula. This differentiation formula tells us that the indefinite integral of 1 over x is equal to the natural log of x plus c. Please note that we have an absolute value here. We need an absolute value here because the domain of 1 over x is all non-zero x, while the domain of log x is all positive x. After putting an absolute value here, we have extended the domain of log x from all positive x to all non-zero x. That means now their domains are the same. There is no need to bother the absolute value in the case of differentiation because the domain of the differentiation is all positive x, and 1 over x can carry all positive x, so that's not a problem. However, there is a problem in the integration because the domain of this integration is all non-zero x, but log x cannot handle all non-zero x, so we should add an absolute value so that this natural log can handle all non-zero x. Even though we have an absolute value here, the result of differentiating this is still 1 over x. We can try to prove this integration formula by differentiating log absolute x. By differentiating this, we can consider absolute x as the square root of x squared. Therefore, we can get that the derivative is still 1 over x. On the other hand, by taking a look at this simple differentiation formula, we can have this integration formula. That means the indefinite integral of e to the power x dx is equal to e to the power x plus c. By knowing these integration formulas, now we can take a look at 3 examples and see how we can do simple indefinite integration. In the first example, we need to integrate 2x minus 1 times x plus 3. Please note that we have product rule in differentiation, but we have no product rule in integration. Therefore, we have no choice and we must expand everything. Afterwards, we can split the indefinite integrals and then take out the constants. Now we can apply these integration formulas to obtain a result like this. Please note that there is no need to write down this plus c for all the integrals. We just need to write down the plus c at the end. As a result, this indefinite integral is equal to 2 over 3 times x cubed plus 5 over 2 times x squared minus 3x plus c. Next, let's take a look at this example. In this example, we should first of all consider root x as x to the power 1 over 2 and then 1 over x cubed as x to the power minus 3. Now we can apply these integration formulas. Please note that this formula is still true when n is equal to half or minus 3. Therefore, we can obtain the result of this indefinite integral like this. Finally, let's take a look at this example. In this example, we need to integrate a rational function. Please note that there is quotient rule in differentiation, but there is no quotient rule in integration. Therefore, we have no choice and we must expand everything. Now we can consider these integration formulas. For 5 over u, because the power of u is equal to minus 1, therefore we cannot apply this formula and we must consider this formula of natural log. As a result, the indefinite integral is equal to this. This is how we can do basic indefinite integration.